Hi kids, today we're going to look at reactions 7, 8, and 9. So let's deal with these first ones, reaction 7. So it's zinc plus copper sulfate. So I've got that set up like this. Zinc is a solid in there, and copper 2 sulfate, it comes as a dried chemical like this. And when you put the copper 2 sulfate into water like you did last night, so I thought it would maybe be blue all the way through it, but I'll give it a little knuckle bust here. Make a whirlpool. There's my copper 2 sulfate. So you can see it's blue all the way through. And when you put those together, does a reaction occur or not? Well, I see that there's some blue stuff in here. So that's copper 2 sulfate, copper 2 nitrate, copper 2 chloride. They're all this color because that blue is due to the copper 2 ion. And then at the bottom, I had some nice silvery colored zinc in there, but now I see that it's changed color. Something funny has gone on here, and let me just let it settle. That reddish stuff, well, that's the color of a penny, so that's copper. And then as I look at the solution, it's not as blue as it was a minute before. And I probably should have come in a while ago and started this. But anyway, you can see that this solution is pretty clear in color. That is actually zinc sulfate. So let's see if we can figure out the reaction here. Zinc, when it's a solid, S, is the silver. It's a metal, it's got a charge of 0. And then copper 2 sulfate. So copper is from the middle of the periodic table, so we need to use the Roman numeral 2 to tell people that the charge is 2 plus or plus 2. So copper 2 sulfate, and then sulfate, you know that from your flashcards, it's SO4 2 minus. Let's say you forgot what sulfate was. Well, you know, little Janie was a chemist, little Janie is no more. What she thought was H2O was H2SO4, H2SO4. You can't forget that rhyme, right? So if you're thinking like, all right, I know that that's sulfate, SO4 is a sulfate, what's the charge on it? Well, you know that there's 2 hydrogens attached to it. H has a +1 charge because it's in this first column, the 1A column of the periodic table. And there's 2 of them. So H has a +1, H has a +1. So that means sulfate has to have a -2 charge. You could crisscross applesauce and have a 2-to-2 ratio, which is the same thing as a 1-to-1 ratio, but we don't write one. So it's just CuSO4. That's a reaction did indeed occur. Solid stuff that's in the bottom of that test tube now, it's reddish in color. That's copper, Cu with a 0 charge, just plain copper like a penny is made out of. And then we have some sort of zinc sulfate, SO4. So zinc, it's from the middle of the periodic table. I don't know what the charge is. Wait, I do know what the charge is. It's on my flashcards. It's a +2. Sulfate is a -2, +2, oh, we're good. So let's balance it. 1 zinc, 1 zinc, 1 copper, 1 copper. 1 sulfate is one thing. Sulfate is one thing. We're good. It's a 1-to-1 to 1-to-1 mole ratio. Why did this reaction occur? Looks to me like when this reaction was done, zinc was with a buddy. I suspect that when we look at this list of the activity series, we're going to find that zinc is farther over here toward the lithium side than copper is. Zinc is right here, and I see copper is down here. Yes, zinc is more active. Let's look at this next reaction. It's copper. So I just took some copper turnings is what they're called. I like these turnings because they have a lot of surface area. All right. And then I took some zinc sulfate, so it comes in a little, it's white powder. And when I put it in water, it's a nice clear solution, which by the way is the same solution as in the last reaction, even though it hasn't quite cleared out yet. And then here's the final results. Last night, I had this all set up, and I took some copper, and I took some zinc sulfate, and I put them together. And let's look what happened. Nothing. Didn't react. Which is, of course, what we suspected, right? Because copper is already lonely by itself when we put it in. And today it's still lonely all by itself because zinc is dancing with sulfate still. Zinc, so there was no reaction. Write down NR for no reaction. Here's what we tried to make happen. We took copper, solid, plus zinc sulfate, And we thought maybe it would make copper 2 sulfate plus zinc. But that didn't happen. So copper 2 sulfate, we know that that's blue. There's no blue aqueous solution in there, right? Is there any silvery colored metal that precipitated to the bottom of this? Or maybe it's floating if it has a low density, which it's a metal, so it probably wouldn't. But yeah, no, that's not in there. Nothing happened. NR, no reaction, is what we write down. Let's try one more single replacement reaction. Copper plus silver nitrate. So we take copper Cu plus silver Ag nitrate NO3. So Ag, silver, is from the middle of the periodic table. It's right over here. It's from the D block of the periodic table. On our flashcards it says that, hey, silver always gets a +1. So it gets a +1 if it's bonded to something. And then nitrate, that's a flashcard one, NO3, -1. So we have a +1 and a -1. Works together, works just right. AgNO3. If there's a reaction, this would be a single replacement. Copper fights with silver. If there's a reaction, we would suspect that there would be some copper nitrate. If it's blue, that would be copper 2. And then silver, Ag, would be out by itself. It's a single replacement reaction. Who should win, copper or silver? Copper is here. It's not terribly reactive, but silver is almost as unreactive or non-reactive as gold is. It stays as just plain solid silver, shiny, beautiful. It's great stuff. I suspect this reaction will occur. You got the plain copper turnings, Cu with a 0 charge. Silver nitrate, AgNO3, when we put it in water, it dissolves, so it's aqueous. Anything that has nitrate attached to it, it's always aqueous. Last night, I took the silver nitrate and I poured it into the copper, and let's see if anything happened. Something happened. Oh boy, I wish you could see this. Right there, you can see that there's some pretty little crystals that occur, that are made here. You should look up silver crystals, just Google it, and you'll see that it looks like little Christmas icicles or something. So there's still some copper in there that hasn't reacted because I didn't add enough silver nitrate, I guess. But if I did, all the copper would seem to go away. Another thing that you can sort of see here is that solution, copper 2 ions. So this reaction did indeed go, and we predicted that it would. One little change here is this. Copper is blue, so I'm pretty sure it has a +2 charge. Nitrate has a -1 charge. So if we crisscross applesauce, here's our formula. CuNO3 in parentheses 2. 1 copper, 1 copper, 1 silver, 1 silver. 1 nitrate, 2 nitrates. Uh-oh, I can only put a 2 here in front of the silver nitrate as a coefficient. I just wrecked my silver numbers. 2 Ags on the left, only 1 on the right, so I can put a 2 right here. Please do not put a little 2 in the bottom. That means that they're bonded together. They're separate silver atoms. Let's take a look at the reaction set number 8. It's copper plus nitric acid. Does anything happen? So I'll put some copper there, and we're going to add some nitric acid. So acids always begin with an H, right? There's H2SO4, there's HCl, there's C2H3O2, and there's HNO3. If this reacts, it looks to me like we're going to get a single replacement reaction. We have H as part of an acid fighting with copper. Will a reaction occur? Let's see. Now, if it does occur, I predict we'll get a CuNO3. If copper has a +2 charge, which it probably will, then we'll need 2 nitrates, but we'll see if we get a blue solution. And I think that we'll have hydrogen gas. Be careful, because something weird might just happen. Nitric acid. And I'll use my pipette and pipettor and suck some of that stuff up. And you can see that there's some nasty brown colored gas that's being made. Oh, turn on the fume hood. Did a reaction occur? You betcha. Alright, a reaction certainly occurred, but it's not really what I expected because hydrogen gas, when we made the bubbles the other day, we had the explosion in the bubbles, that was hydrogen gas, and that hydrogen gas that was coming out of there was clear as could be. This gas is like some sort of weird brown stuff. There is some copper 2 nitrate, CuNO3 copper. There's blue solution there, so I think it's copper with a +2 charge. Nitrate with a -1 charge, so we need 2 of those, CuNO3 2, in parentheses, NO3. And the brown gas is NO2. There are some other kinds of nitric oxides that are being formed there as well, but the main one is NO2 gas, and that is the brown stuff. If you ever go to a very polluted city, Los Angeles used to have a lot of this NO2 in the atmosphere back before the environmental changes of the 1970s. It was a horrible place, the smog of California. If you go to Mexico City, there's still quite a lot, but they're getting a handle on that. Delhi is the place that I've seen this, a lot of this. There's also some water that's made here, so H2O. If you're trying to balance this reaction, it turns out that it's a difficult one to balance, so I gave you the balanced reaction. I'm asking you to write the skeleton reaction, so make sure you know what a skeleton reaction is. It's super easy. Just take away the coefficients. Take away the 4, the 2, and just rewrite this and you'll have your skeleton reaction. There is some single replacement going on here, but mostly it's going to be a decomposition reaction. 1990, I went into the Peace Corps and I went to a country called Nepal. My village that I went to was called Gara. It's near Pokhara, Nepal, if you want to look it up. It's up in the mountains. I met my family, the Badarwals, and they were super nice. So I spent a lot of time reading books, and I'd read books at night with my flashlight, and eventually my batteries died out. The mother of the Badarwal family came over one night, and she brought with her a little cup about like this, and she brought with her some kerosene. It's a type of fuel. Then took her sari, her dress, which is her old, beat up working around the house dress that she used for cleaning up, spills and cleaning kids' butts and washing the dishes and things like that. So it was kind of tattered and there was just ripped off a little bit of it, about like this. And she dunked it into the kerosene, and then she took a salai, a match, started a little flame, and that's what I used to read by for the next 2 years up in that beautiful village. There's a chemical reaction going on there, and let's see if we can figure out what that reaction is. Put out the flame by taking away the oxygen. So now the reaction cannot proceed without oxygen. That's a fundamental way to put out flames. Kerosene is a petroleum product. So it comes out of the ground, people pump it out of the ground along with gasoline, and it's a big mixture of lots of different things. With kerosene, we mostly have 3 types of molecules, C12, C13, and C14. C12, H26. Well, we know that this was a combustion reaction. It was burning. There's our fuel. We need oxygen, which comes out of the atmosphere. Oxygen is always O2 if it's not bonded to something else. And when a combustion reaction occurs, we always get CO2 and H2O. CO2 plus H2O. And this is an interesting balancing problem. So we have C12, and so we need 12 carbons over here. So I'll put a 12 right here. All CO2s. We have H26. So 26 hydrogens, we have sets of 2. H2O always has 2 hydrogens. So if we have a 1 in front of this, we have 2 hydrogens. If we have a 2 as a coefficient, we have 4. If we have a 3, we have 6. We always have even numbers of hydrogens on this side. 26 means we have 13. But what we just did was caused a problem for ourselves. We now also have 13 sets of 1. That's an odd number. Over on this side, oxygens always come in pairs. We have an even number on this side, we have an odd number on that side, but there's a trick. When you have odd numbers of something on one side and even numbers on the other side, what you do is you double everything that you've already done. So I had a 1 right here as a coefficient, even though I hadn't written it. I'm going to make that a 2. I had 12 right here as a coefficient. I'm going to make that 24. We had 13 right here. I'm going to make that 26. I just doubled everything. But when you double things, they always turn into even numbers. And so now we have 26 sets of 1 O. That's easy. 26 oxygens. So how many sets of 2 on this side give me 26? And that's 13, right? You have to balance two more reactions here. C13H28 and C14H30, I believe. The C13H28, you're going to find out that you don't have to use this doubling trick, but when you get down to this last one, you're going to run into the same problems we just ran into with the even-odd thing. And remember, what do you do when you have an even-odd problem? Double everything. It's pretty cool. All right, so thank you guys for your attention. I hope you liked all these reactions. I wish you could all be here and see them in person and help out and things. But bye-bye.